Okay, so right, just a quick reminder of what we did last time. These things I have written up already, but it's what was written up before. So, so this is just a delta ring here. Then these are the axioms for a delta ring. So P is a fixed prime number. And I call these the Leibniz rules for delta, for addition and multiplication, and for 0 and 1, if you like. And recall that the delta x, I don't think I used this term last time, but I think it's a nice term, is a witness to the congruence. Because phi of x is x to the p plus p delta x. So we somehow, it's a witness to the congruence. Then if you iterate delta n times, then you can just, in principle, expand out what this sum is applying these rules again and again, and you get some big polynomial expression in the lower iterates of delta applied to x and y individually, and similarly for multiplication. And now the key point is that these
Jim, just to be clear, when you do the second higher iterates, it will involve both the multiplication and additive iterates. Right?
Yeah, exactly. So
quite,
I mean, it's almost, I don't know if anyone has ever even determined these explicitly for n equals 2.
Okay.
Right, because I mean, I think there's not even maybe really a closed form. I mean, for a given prime like 2, it might not be so bad, or if p equals 3, it might not be so bad. But for a general prime, then the number of terms in this sum, depends on p.
Right.
So yeah, I don't know. Maybe it's not so. I think it would be unwise to do it this approach, but maybe it's not so bad to do it some other way. But yeah, you have to use all 4 of these rules repeatedly. And now a key point is that these, as I was saying, these the Leibniz rule for addition and multiplication are unique. They're the unique polynomials. So one has to check that, but that follows from the case where p is invertible pretty easily. And then the Witt vectors are defined to be just an infinite product of copies. The Witt vectors of A are defined to be the infinite product of copies of A, and the addition and multiplication are defined exactly in terms of these Leibniz rules. So that in the nth component, it's just given by the same polynomial, but now you evaluate it at the preceding entries. And here's what 0 and 1 are. Delta, of course, just shifts to the left. And then the universal property is that if R is a delta ring, which has a homomorphism just to a ring, then there's a unique lift of that homomorphism to a delta ring homomorphism to the Witt vector ring. And another way of saying that's just what it means for W to be the right adjoint of the forgetful functor from delta rings to rings. Okay, maybe one thing I didn't say last time is that, see, that there's a traditional approach, which I'll mention today. In the traditional approach that you find in all the books, this is given by an explicit construction with formulas. So one problem with that is that if you ever want to prove anything about Witt vectors, you're reduced to proving something about the formulas, because that's literally how they're defined. And people kind of think of the purpose of Witt vectors is to lift algebras over FP to characteristic 0. Well, I haven't explained how you have something over, if A is an algebra over FP, how you get something in characteristic 0. I'll say something about that today, but maybe people have heard this before. Whereas this approach here, I say our approach, but it's kind of maybe originally due to Joyal, is that it's given by a simple universal property. So there's kind of no formulas. At least conceptually, there are no formulas. And the purpose is not so much to lift something to characteristic 0, but to provide a delta structure. And a delta structure I think of as really just an intelligent way of talking about a lift of Frobenius. So it's really, the purpose is somehow to provide a lift of Frobenius, not so much to lift the ring. So it's still an interesting concept, even in characteristic 0 if you have just a general ring. And a kind of a key point is that unlike in the traditional approach, in this approach, no lemmas about p-adic congruences were required. So in the traditional approach, you kind of have to prove some, maybe not so hard, but not so easy lemmas about p-adic congruences to make the definition work. Whereas we didn't have to do any of that with this approach. Okay, and then here are these references, which I gave last time, 3 different references. Okay, so that was just a quick review of last time. Actually, I could pause if there are any, see if there are any questions before I launch into new things. Okay, so now I have to bring up my notes. Okay, so yeah, so one thing it really kind of belonged in the last lecture, but let me say it. So this is a moduli interpretation of the universal property. So suppose that that we have, so R is a delta ring, and now X is the spectrum of R. Then what do we have? Then if A is just some other ring, then the A points of X, by which we just mean the homomorphisms from spec A to spec R, which are just, of course, just the same thing as the ring homomorphisms from R to A. So this is the situation we were in up here, exactly the ring homomorphisms from R to A. And they're in bijection with the delta ring homomorphisms from R to W of A. That's the universal, that's exactly the universal property. So this is the, I'll write it this way, the delta ring homomorphisms from R to W of A. And then those are particular examples of just ring homomorphisms from R to W of A. So in fact, it's terrible. That injects in here because these are all the ring homomorphisms from R to W of A. So what we get is we have just composing that, we have a canonical map that from the points with coordinates. So this is a little funny, right? Because WA projects onto A, and there's rarely a map going backwards. Yet, because we have a delta structure on R, we can, if we have, so let me put it this way. Therefore, if a moduli space has a delta structure, then the objects it classifies have a theory of canonical lifts. Lifts to W, say to classify sort of over A. So for instance, if you had, I mean, I'm talking about affine schemes, but let's just say we did projective schemes or Grassmannian or something. Grassmannians don't have delta structures, but projective spaces do. Then it says if you have a kind of a line, a projective space classifies lines in a high dimensional affine space, then such a thing can be lifted to a line in the Witt vectors. So this is most famous in the case of elliptic curves. So for example, elliptic curves, or the so-called ordinary elliptic curves, if you don't know about elliptic curves, then don't worry about it. I won't mention it again. So lift canonically. So this is the famous canonical lift in the theory of elliptic curves, but in fact this works over any base. So lift canonically, so maybe I should say this, over any base. So in this case, the moduli space X would be the modular curve with appropriate level structure, and it does have a delta structure. And then somehow automatically, this gives, so a delta structure on the moduli space gives you a machine for lifting objects that the moduli space classifies over a ring A to objects over the Witt vectors of A. So this typically, in many cases of interest, A will be some algebra of characteristic P, and then W of A will be an algebra of characteristic 0. So it's kind of a funny thing. It allows you to lift things canonically to characteristic 0. Okay, so maybe I'll give, so this is, maybe I'll give a citation here. This is a paper I wrote with Lance Gurney, which is, the archive number is this. So somehow, I guess the reason why I find it interesting is because, I don't know, maybe canonical lifts of elliptic curves in characteristic P from characteristic P to characteristic 0 is kind of a mysterious thing, but kind of the point of view I like is that the explanation is simply that the moduli space of all elliptic curves has a delta structure of all ordinary. Sorry, I said characteristic 0. Characteristic P. Okay. Okay, so now let's kind of,
sorry,
that was
is
a little
it clear why the projective spaces don't have a delta structure?
Projective spaces do. Well, first of all, we have to be a little careful because I've only defined delta structures for rings or for affine schemes, not for non-affine schemes.
Right.
Grassmannian, it's Grassmannians that don't have, so there's a theorem due to Paranjapa and Srinivas theorem. Which is that if the only flag varieties over ZP with Frobenius lifts are projective spaces. So in a projective space, you do have a Frobenius lift because you just take the usual homogeneous coordinates and elevate them all to the pth power. And that gives you a well-defined map on projective space, and it manifestly agrees with the Frobenius map in characteristic P. So that is a that does have a Frobenius map, and then once you define the notion of a delta structure on a scheme properly, then you see that is in fact a delta structure on the scheme, but on projective space. So projective space does have them, but Grassmannians and other flag varieties don't.
Thanks.
Yeah, okay. So now let's talk about the category theoretic package. I mentioned this a little bit before. So we have, if C is just a general ring, possibly non-commutative, we have this forgetful functor. We have the left adjoint, which is this. We have the right adjoint, which is that. And remember, I also talked about differential rings, which is just a ring equipped with a derivation. And then there's forgetful functor to all rings. There's a left and a right adjoint. The left adjoint was what I called the differential Witt vectors, which were just divided power series. And then the right adjoint, the left adjoint, let me call it this. I'm just introducing a symbol there, and I'll tell you what that is in a minute, but it's something like a tensor product. That's why I use that symbol. And then finally, we have delta rings, forgetful functor to all rings, this is the one we really care about. This is the usual Witt vectors, and this will be something similar to the free differential ring functor. This will be the free delta ring functor, and it will be some kind of generalized tensor product. So I'll talk about some things in all three of these cases. So give them labels, A, B, and C. So A is meant to be very familiar, B is meant to be not so hard, but ring theoretic, and C is meant to be the one we really care about. Okay, so A, so we can think of C. Of course, it's introduced, we know what C is, but if we didn't, another way to think about it is the free C module on one generator, which one typically just calls one, the multiplicative identity of the ring. Another way to think about it is the set of natural one-ary operations on C modules. So to every, more properly, it's the endomorphisms of the Forgetful functor. So to each C module, you have a natural endomorphism of it, which is just multiplication by an element, little c of big C. And then you prove, not so hard, that the set of such natural endomorphisms of the Forgetful functor, the natural one-ary operations on C modules, is exactly the original ring C. So you can recover that kind of from the category theoretic setup. And another way to think about it is the representing object for the right adjoint.
So natural one-ary operations just means the endomorphisms of the Forgetful functor.
Yeah, exactly. Endomorphisms of the Forgetful functor to abelian groups. I don't know if you took endomorphisms of the Forgetful functor to sets, I still think you would get the same answer. I think, yeah, so I guess there's one, you could say the natural linear one-ary operations, that would be endomorphisms of the Forgetful functor to abelian groups, or you could just say all natural one-ary operations. And I think, yeah, I'm sorry, it's been a while since I thought about this, but I think you get the same answer.
Yeah.
And I think this is kind of the one that I more want to consider for the next steps.
But is the last one sort of a circular?
Sorry?
C is the representing object for the right adjoint on C.
Yeah, exactly. It's kind of dumb. But if you didn't know, if you were somehow just given this as an abstract category with a Forgetful functor here and then two adjoints, you could recover it.
Yeah,
C
yeah, okay, I see.
From that. So that's the point. You can recover C from either the right adjoint or from the left adjoint, purely from the category theoretic setup.
Okay.
What is C?
What is C?
Yeah.
I mean, C is just an abstract ring, and a general ring.
Okay, a general ring. What is that?
A general ring. So it's a little stupid because I've set it up as if we already know what C is, but if
okay,
we were
but
given,
it's commutative or?
Oh, it doesn't have to be. It doesn't have
have to be. Okay.
Okay. Oh wait, I think I wanted to say one more thing. And then yeah, so then the left adjoint. The left adjoint construction applied to an M is of course this, and it's generated by symbols. I'm not saying anything that people don't know. Then mod relations. So this is something very familiar. Maybe it'll start to be less familiar when I go to context B and C. Okay, so in this case, in this case, we actually don't have, unlike that here, C was built, we knew what C was. Here we just have some category. It's not defined to be somehow the representations of some abstract object. It's just a ring together with a derivation. But in fact, we can think of it that way. We can think of it as representations of something. And we do this by saying we let D, so I guess this is now a definition, is the free differential ring on one generator. And up here, I mean, one was really the kind of, I don't want to use, rings already have an element one, so it would be dangerous to call the generator one. It's best to call the generator E, which is the identity operator. We kind of think of it as the identity operator, just like one in a ring is the identity operator, say in any representation, any module over that ring. And now let me explain the second point of view, the natural one area operations. So that'll take just a line or two. So suppose you have, so what is this, this thing? So this is, of course, just, so we have the generator E, and then we have D is meant to be D of E, and then we have D of D, and then we have, I mean, these can just be viewed as symbols, but right, the D sends. So that's that's the free ring on one generator with a derivation. So these are just polynomial expressions in these symbols here, but we think of these symbols as kind of iterates of D, because it's, I guess if you like, it's you know, D composed with itself n times applied to E. So we kind of think of them as iterates of D. In other words, you can kind of think of them as nonlinear differential operators. So, and in fact they are. So, so suppose, how does that work? Suppose you have some polynomial expression in these Ds. This defines a natural operation on differential rings. And how does that work? So let me just give you an example. And I chose an example, which is the numerator of the Schwartz derivatives, because to show that these things actually, people care about them. So this will be like 2 times the third derivative times the first derivative minus 3 times the second derivative squared. So this is the numerator of the Schwartz derivative, so, that people in Teichmuller theory care about. And then now, how does this act on? So this defines a map which sends, defines, say R is a differential ring. It defines a map from R to R. It just sends an element to 2 times the third derivative of f times the first derivative of f minus 3 times the second derivative of f squared. So one thing to keep in mind that's also going to be relevant in the delta ring situation is there are kind of 2 operations here. There's multiplication, and then there's composition of operators. So right, you see it right here. D composed with itself 2 times is the second derivative operator. This exponent here is the squaring operator. So unlike in normal algebras, normal algebras act on vector spaces. There's no multiplication on vector spaces. So normal algebras just have composition and addition. But now our things will act on rings, and rings have both addition and multiplication. So now we have addition, multiplication, and composition of operators. So you see that, you see this right here. Okay, so it's a little exercise to show that D is the same thing as the natural one area operations on differential rings. Or more properly, it's the endomorphisms of the, I'll give this forgetful functor here a name, U. So it's the endomorphisms. Actually, it's the, we have to be careful, like, because see, these will typically be neither additive nor multiplicative. So it's really the, maybe it's dangerous to call that U. It's the forgetful functor to sets, what I really want. So endomorphisms of the forgetful functor from differential rings to sets. So each,
what is R? What is R in your example?
R is a differential ring. So for any differential
every
ring R, if you're given such a polynomial expression, which we think of as an algebraic differential operator, just syntactically, then if you have a ring with a derivation on it, this symbol, this polynomial defines an operation, a functorial operation. And it just sends an element of R to this expression here.
So I suppose what you really want to say is that the polynomial algebra generated by D is the endomorphism.
Polynomial,
The
no,
right-hand
this
side
is,
there is a ring, right? So Z.
let's see, which,
The
it's
last
much
line.
so this is a polynomial algebra and infinitely many variables.
On the last line.
Here?
Yeah, so the left-hand side should be an algebra. So the left-hand side of that, at the very left of that line. D.
The left-hand side.
Yeah.
Even it is an algebra.
To the left.
Further to the left, D.
Yeah.
Yeah.
So D generates this over. D generates this ring of endomorphism.
No, it's the whole thing.
Oh, sets. That's why you took sets, is it?
Yes, to sets, exactly.
Okay.
So these are non-linear, natural.
What happens if you take rings?
Then it would just be the operators which are both additive and multiplicative, and that would be, I think, only the identity operator. Because even the first derivative map does not give a ring endomorphism. As a Leibniz rule, if you took the forgetful functor to abelian groups, then it would be all linear combinations of the nth derivative operations.
ZD, polynomial algebra.
Yeah, exactly.
Okay.
But now we want to take all polynomial, those would be the natural linear operations, but now we even want nonlinear ones. So you take an element of a differential ring, you take its derivative and then square that. So that's something which is not at all additive or multiplicative.
And related to Uri's question, now that is what you've written down is D evaluated at R, right? The natural transformation. D evaluated at R takes is the D operator on R.
D evaluated at R.
D is a natural transformation, so you evaluate it at every object in the category. And
D is the set of all natural transformations.
Oh.
So what I explained here, so maybe it'll be a little
confused then. Okay.
So there's a bijection. So this will take C to ... So what I explained here was, if you have an element of D, which is a polynomial expression like this,
okay.
It will give you an endomorphism of the, well, let's just say a natural endomorphism of any differential ring, and in this case, it will but it's an endomorphism in the category of sets.
Yeah. Okay. I think. Okay. Fine.
So it takes this. It takes this to this, which is just a map from that set to that set, but it uses the ring structure. I have a feeling people still, this is not the first time that when I've given this lecture, people have kind of insisted for clarification here. So please continue to ask questions if it's still not clear.
So if I take an element of D, then it is okay. So it's an element of this free differential ring, and
Yes.
basically D circle I will be the dth iterate of the derivation on any R. Right? So
That's right. That's right. So the point is, yeah, okay, thank you. Maybe I should have said that. So D circle I goes to the, this is initially just a symbol. It's a formal symbol. So it's the ith iterate of D on a general differential ring, which is a functorial operation. And then you extend to all polynomial expressions in these just pointwise. I'm still getting some funny looks, but maybe I'll continue. But maybe when I'll do the delta ring.
Since you asked for clarifications, let me seek one. So this D is equal to end of this forgetful functor differential ring to sets. That equality is as differential rings.
I guess I'm just saying it's a bijection for now.
Mm-hmm.
I mean, but since it's a bijection, kind of all the structure.
No. The question is on this endomorphism, that is the set of natural transformations of that functor.
Yes.
Is there a differential ring structure?
Isn't that just a monoid?
Yeah, a priori it's a monoid, but under composition. But of course you can add to, because these things do have ring structures. So you can add two of them pointwise. You can also multiply two of them pointwise. So it's a set with it's a ring together with some extra composition structure on top of that, which is neither the addition law nor the multiplication law. It's the composition law. So because for differential operators, you can do three things. You can add them, you can multiply them pointwise, or you can compose them. And they're just completely different things. So
then
yeah.
as Raghavan is saying, but yet that ring has a differential structure on it. Since you've already told us what it is.
You can post compose with the derivative operator, and then that will give you a new endomorphism of the identity functor, right? Because if you have something here which is natural in R, you can then post compose with D, and you get a new thing which is still natural in R.
Okay.
Yeah, it's a little. The reason why it's because this is an unfamiliar algebraic structure. So you have three levels: addition, multiplication, and composition. And the addition and multiplication are of course commutative, but composition is not. It's really just something different. But if you think about all polynomial expressions in all the iterates of D like this, I mean that's what it is. So that's maybe a good thing to keep in mind. But to compose two operators which are complicated like this, then you have to use all the Leibniz rules, and it's kind of a big mess. Okay. Let's right. Okay. So now the point is that what did I want to say? Yeah. So D, we can say this is maybe I did write this, nonlinear algebraic differential operators. I don't mean literally nonlinear. I mean not necessarily linear. So that now the point is that D actually represents W diff, and that's kind of, it's actually a complete triviality, but let me explain it. So the Helms the ring Helms from D to A. These are D is a polynomial algebra in countably many variables. So let me just write that out. So this is Z, E, E, not. And so you can, there are no relations among these variables, these generators. So you can send any of them to an arbitrary element of A. So this is just the the first one, E goes to one element, and this, and so on. And precisely, just let me make it precise because we're going to need this in a minute. Such a homomorphism will go to the vector, which is just alpha at the first generator, alpha of the second generator, and so on. So this is a bijection.
Sorry, I'm a bit confused. What is that ring? ED dot dot dot.
This is D. This is D. It's just this one up here.
Oh, okay. Sorry. Yeah.
Yeah.
Okay.
Yes, yeah. Yeah. The notation is a little idiosyncratic. Maybe maybe it'd be best to call it D circle N. So E is meant to be when N is 0.
Yeah. Sorry, I just didn't recognize the pattern from tutorial.
Yeah. Okay. Okay, let me finally say, so this is sort of what we care about at the moment, but let me just tell you what this left adjoint is now. D circle A will now be, it will be generated by symbols from here combined with symbols from there, like a tensor product. So let me just write it this way, where so N is at least 0 and A is an A. But now it's generated as a ring. Up here, of course, this is generated as an abelian group, but that was because this was AB, but now we're on rings. So we have to have generated as a ring. And now what relations do we have? We have all the Leibniz rules for these iterates. So the nth composition of D evaluated at AB will be, I mean, this one I can write out in closed form. I'll do it just for fun. And then we have another one for all sums. Of course, these are the sums are just linear, so that one's easy. And then that is that. And then the nth derivative of 1 is 0 unless n is equal to 0, in which case we get 1. So it's just the Kronecker delta. So it's some ring with a huge presentation like this. In fact, it's enough to just restrict to generators of A, but maybe as an abstract definition, it's cleaner to take this, and then it's quite easy to see that this, and then, so then the derivation, of course, maybe I should say that. So this has a derivation, and it will take the formal nth derivative of A to, so these are just formal symbols, right? To the n plus first derivative of A. And then it's somehow cooked up. So exactly, so that this is the left adjoint of the forgetful functor. So this is the free differential ring on A. Okay, now we can move to delta rings. So the whole purpose of that was just to get warmed up for delta rings. So now we'll let delta be the.
Sorry, can I
yes,
ask?
Please.
This form as rings between D and A is isomorphic to this A cross A cross A cross A.
Yes.
this is just a sets, or are you thinking of some other structure?
Yeah, it's just a bijection. However, this was, remember, this was what we called W diff A, which was the set of divided power series. And the coefficient vectors correspond to the components here. So the ring structure, the ring structure here is the obvious one. That induces a not completely trivial, but not so complicated ring structure on the product as vectors. And in fact, it's an isomorphism of rings.
Okay, I missed the last point. It's an isomorphism.
Then the last one would be an isomorphism of rings. Yeah.
Sorry, again, I missed it. Isomorphism as, what did you say? As with what structures?
Rings.
So rings. Okay.
Rings. Yeah.
Okay,
But,
thanks.
yeah. I mean, well, then you have to say, why does this have a ring structure? Some of the rings, and in effect, the reason is because this is a bijection and this has a ring structure. So I think the point is that it's a bijection. That's the ring structures match up is kind of a secondary issue that it depends on how exactly you define the ring structure on this, but maybe one of the most natural ways is just to define it to be the one inherited from this bijection.
So this is not the Om rings D2A. I mean, once again, because A is a ring, you can pointwise multiply and pointwise add. That's not the one.
Yeah, because then that won't be a ring homomorphism.
Yeah, that ring won't be a ring homomorphism. Yeah. Okay.
Yeah. So it's like, maybe I should say this. So there are two. This means the spectrum of D will be not an algebraic group, but an algebraic ring. And there are two operations. There are two co-multiplications, which correspond to the additive structure and the multiplicative structure. And you can say what those are. And in fact, they're just another way of saying what the Leibniz rules with respect to addition and multiplication are. But you have these two co-operations on D, and then this will inherit this set of ring homomorphisms from D to A will then inherit two operations, which we call addition and multiplication. And because these satisfy the opposite of the ring axioms, this one will satisfy the ring axioms. And then if you say it all that way, then this composition from here to here will be an isomorphism of commutative rings.
Thank you.
Okay, I'm a little concerned that I'm making sound a little more complicated than it. Okay, let me continue. So we just define now delta to be the free delta ring instead of differential ring, free delta ring on one generator, which we again call E. So this is just of course, E is the same thing, just notation, the zeroth iterate of delta. And what is the delta structure on here? Because this is just a polynomial ring, we can define delta to do whatever we want on the generators. So just as in the differential case, we define delta this way. So another way to put it is the Frobenius. The Frobenius map corresponding to the delta will send this symbol here to its pth power plus p times delta of it, which should be delta n plus 1. So this, if you like, so why can you define these deltas arbitrarily? Because we define this Frobenius endomorphism arbitrarily on the generators. That's certainly allowed. And look, it is in fact a lift of the Frobenius map. It's congruent to the pth power map modulo p. So therefore it defines a unique delta structure on this ring. And that delta structure is exactly the one which sends the nth iterate of delta to the n plus first iterate of delta.
When you say this ring, you mean that, of course, the ring structure is the one that makes this be.
Let's see, this, here, this is just the normal polynomial ring on infinitely many variables.
Oh.
Yeah. So this was, we're kind of doing the left adjoint now rather than the right adjoint. Right, because a homomorphism, why is this the free? So what is it? What is a delta ring homomorphism from into a delta ring? Well, wherever you send E, everything else is determined because all these higher generators are just delta of the lower ones.
And
So
why is phi always a ring homomorphism? Is that?
Okay, in a delta ring.
You're only defining it on a generator, so.
Yeah, that's right. That's right.
Okay.
So this is defined on generators, so it extends uniquely to a ring homomorphism.
Okay, I get it. So it may be hard to write down what phi does to a general element, but.
Yeah, it won't be so. No, it won't be so bad for phi for delta because it, you know, if you so phi of a general polynomial in I don't know. Let's see what. Maybe I'll call them x's. So the variables will be x's would just be you just substitute in these right here. So it would just be f of delta 0 to the p plus p delta 1 comma delta 1 to the p plus p delta 2 and so on. I mean, if you have a map from a polynomial ring to any other ring, and you know what it does on the generators, it's easy to say what it does on a general polynomial. Okay. You just substitute.
Okay, I guess I was overthinking it. Yeah.
Okay. Right. So this I would like to call the nonlinear P differential operators. So the ring of nonlinear P differential operators. So you can, again, you can add, subtract, multiply, and also compose them. And then you can also check, so maybe this is an exercise, this is in bijection with the set of natural one-ary operations on delta rings. In other words, endomorphisms of the forgetful functor from delta rings to sets. And once again, delta represents W, and how does it work? It works exactly as before. So the ring homs from delta to say a ring A. So what is delta? It's this ring. And now we just evaluate those generators, that homomorphism at the generators, and we get a vector of elements of A. So this takes alpha to alpha of E, alpha of delta, alpha. So, and then that's a bijection. So, and this, of course, the whole point is that this is W of A. So you could think of this as, this is kind of nearly this is yet another, maybe even less formulaic definition of the Witt vectors of A. You just take the well, I mean, of course, the Leibniz rules are crucial here, and I'm not mentioning them. If the whole point on, maybe I'm kind of telling you, stretching the truth a little bit, because the whole point on Witt vectors is to define the addition and multiplication, and that depended on the Leibniz rules. And if you try to take this as your definition, which I'm kind of advocating as an alternative form, then, I mean, you're not really saving yourself any effort. You do have to define these Leibniz rules. But maybe it's a slightly more conceptual way of looking, this makes it look like a co-induced. So this is, a co-induced delta ring. So let me go back up here. When we're talking just in the normal situation about modules, if your ring C had a presentation, then you could actually define kind of these functors without even knowing what the word algebra means. You would just define it in terms of generators and relations. And effectively, we did that with kind of the differential rings and the delta rings. And the point of a lot of this discussion down here was to, so here we have a C, and here we don't have something that plays the role of C, but the point was to say, actually, we do. It's the free object on one generator. So D, so maybe we could say differential rings, or then we might call them D rings. And then delta rings are delta rings, which is why I call that delta. So the point of that discussion was to introduce the object that plays the role analogous to C. Okay, and now the left adjoint will be delta circle A, and this will be just like in the differential case. We adjoin formal symbols like this, where n is at least 0 and A is in A. And then we mod out by relations, but now, unlike in this case, we could write the Leibniz rules in closed form up here, and this is so easy I didn't even write it. In the delta ring case, we can't really write them in closed form, but we have our polynomials. So what did I call it? Pn plus of A comma B comma dot 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 comma delta n A comma delta n B, and then we have a Leibniz rule for multiplication, and then for 0 it's easy, and for 1 it's also easy. Again, it's the Kronecker delta, kind of terrible confluence of notation. So this is Kronecker. And this again is so why is this has a delta operation on it, which just sends that formal symbol to this formal symbol, and it defines a delta ring structure. I guess maybe it would take a little bit of an argument to prove, to think about why actually that does define a delta ring structure. The axioms are not trivial, and this might not be P torsion free. So maybe that's an exercise. Okay, are there any questions? I feel like I might.
Sorry, what was the exercise? I didn't quite catch it.
Exercise to show that the left adjoint, that this construction, show that it has a delta structure defined by this. So there exists a unique delta structure. Exercise. Defined by that. the uniqueness is clear because these are generators. What you need a little bit of an argument to show is that they're compatible, so there exists such a delta structure. Okay. So the point, okay, actually, let me, before I get to the main point, there's just one fact that kind of follows formally from all these things that I've been discussing, which is the category of delta rings has all limits and colimits over any diagram, and they agree with those in rings. And they agree with those in rings. So for instance, it has coproducts, which in rings are the tensor product. So the tensor product of delta rings is a delta ring canonically, and it has the same universal property. It has direct limits, it has co-equalizers, and then in terms of the products, it has the limits, it has products, including infinite products, also infinite tensor products. It has inverse limits and equalizers. So any kind of limiting construction you want to do in delta rings, you might think it's a big mess, and maybe it kind of would be, but it's just the underlying ring is just the same limiting construction, and then there's a unique compatible delta structure. So that follows kind of formally from everything I discussed above. Perhaps that's also best left as an exercise. Okay. So now here is kind of the point with the relation with the usual treatments of Witt vectors. So suppose we have a different, so on our delta here, remember where was delta? Delta is this thing. It had a free generating set given by the iterates of the operator little delta. Suppose we have a different set of generators. In the way, so in an algebra, you might have a different basis. In this case, it's a generating set as there are infinitely many as a ring, but it's a free. So it's a free generating set. Then everything I discussed up here would go through the same way. So then Holmes from delta to A are once again going to be in bijection with infinite vectors. So we'll send an alpha to the value of that homomorphism at those generators. Like this, and this is again a bijection. But the ring structure on the right-hand side will be defined in terms of the Leibniz rules for these generators, which these things can be regarded as natural operators, right? Natural operations. So delta is the set in the same way that, I mean, any element, as we discussed up here, any element of D can be regarded as a natural operation on differential rings, and therefore will have its own Leibniz rules with respect to addition and multiplication. And I didn't make that point explicitly down here, but it's true for the exact same reason. So any polynomial combination, polynomial expression in these basic deltas, the iterates of delta, will again define a natural operation on all delta rings. And so each of them will have its own Leibniz rule. It could be a bit, it will usually be a mess if you add the first derivative to the square of the seventh derivative. It will have a crazy Leibniz rule, but it will be some polynomial expression which works on all elements. And so, and these, so which will generally have nothing to do with those for the deltas, nothing to do with those for the delta n. So there are, if you have a different generating set, it gives you just a completely different description of, remember this is W of A, these are the Witt vectors, gives you a completely description, this one over here, of the Witt vectors of A. It's also a vectorial description, but the ring structure will be completely different and will depend on the choice of the generating family of operators you use. And this is the point with the traditional approach to the Witt vectors. So our approach is we use the iterates of delta as generators of this ring. In fact, it's a little bit turning things on its head because delta was defined to be the thing generated by these, but the traditional approach we sort of use some new nonlinear p differential operators. So use new operators theta n. And that, so, and maybe another way of thinking about it is W, which sends A to W of A. This is a ring valued functor on rings. So this gives you a ring scheme structure on infinite dimensional affine space over the integers, if you like. But there are many different coordinate systems you could choose on this. There's no, I mean, I've written it with a canonical one, but there are other canonical ones you can choose. And that's the difference between the approach we've taken and the traditional approach, just two different canonical coordinate systems on what should be viewed as the same object. Okay, so the next thing to do is to tell you what these new operators are. These Witt, these you might call the Witt operators. However, I can pause for questions if there are some.
Hello, sir. I have a question that you just said that when we apply the right adjoint and left adjoint, we get the underlying set of the delta ring is Witt vectors, right? But they have different ring structure.
There are two. Maybe you should compare it to this. Like, suppose we have an algebra and we take a co-induced module like this. This, if C has a basis, then this can be described as a product over, so say it has a basis S. This can be described as a product over S of M. Right? Because C would be a free abelian group, and so the Homs on this generating set S to there are just given by this product. But if you change the basis, so this is not maybe equals is writing it back. So this is one bijection, then you can get a different bijection to another basis S if you choose a different. So say there are two different bases, S and S prime. Then you have this, and the C module structure on these two things will be completely unrelated if these two bases are unrelated. because and the same thing has happened. So there's two kind of vectorial descriptions of this co-induced module, but the relationship between them, like there's no reason a priori why they should have anything to do with each other. Like if the two bases are completely different, then the coordinate style description of the co-induced module will be completely different. And the same thing is happening here.
Yeah, but they are isomorphic modules, right?
Of course, in fact, they're canonically isomorphic.
Yes.
But the rules, if you wrote out the module structure and kind of in terms of coordinates, they would look completely different, and you wouldn't.
Okay, so you are saying the ring structure, addition and multiplication, they are different, but they, as a ring, they are isomorphic.
Yes.
They
exactly.
have to be, right? Because we are taking the forgetful functor.
Yeah. So the two, right. So there's sort of W trad, the traditional A is kind of naturally the same as Holmes from polynomials in one generating set. This is literally the same thing as Holmes from this other generating set.
Yes.
Because they literally generate the same algebra. And then this is isomorphic to ours, W ours. And they're both infinite length vectors, but the map between them, the ring structures are completely different. There's a non-trivial map between them, which is a ring homomorphism. In fact, it's an isomorphism, but
yes.
It's certainly not the identity map.
Yes. That actually I wanted to know. So there is non-trivial isomorphism.
Yes.
Yeah. Okay. Thank you.
And maybe it will help to. I'll be able to write down the first few. It will be trivial for the first two components, and then it becomes non-trivial. So maybe, well, I could launch right into that, or if there are other questions, I could try to answer them. Okay, so now let's talk about the Witt components, or the Witt operators. And so here's the definition. We define theta n's. They a priori they will have p's in the denominator. We will prove that they don't, in fact, recursively by. Okay, so here's the formula. Let me first just write it down and then I'll explain it. Feel like I could put a p to the 0 here. P to the 0 is of course 1. So let me explain this formula. Phi is is it an element of delta? It's the Frobenius operation, and that is it's simply the pth power of the identity map plus p times delta. So this is it's a polynomial, and it's kind of obviously an element of that. It's a degree p polynomial in the first two variables, if you like. And then you can, because you can compose any two of these arithmetic differential operators, you can compose phi with itself n times. And then we have to solve for this. So at the nth stage, we can solve for theta n by, we divide by p to the n. We assume all the previous ones are defined, and that's why we at least a priori need this p to be in the denominator. So one thing to emphasize, however, is that this exponent is iterated composition. The exponents on the other side are just usual exponentiation. So iterated multiplication. So pointwise multiplication of operators. So let me just, I think what actually is most clarifying is just to write down the first few examples, and then I think many people find that much more helpful. So n equals 0. Let me just, it's kind of trivial. You get theta 0 to the power 1. So this is understood to be the identity operator. So therefore, theta 0 is the identity operator, which I've been calling E, but which we might also call theta composed with itself 0, delta composed with itself 0 times. Okay, n equals 1. So then we get phi composed with itself 1 time is equal to theta 0 to the power p plus p times theta 1. And theta 0 is the identity operator. So this is e to the power p plus p times theta 1. But phi is, of course, e to the power p plus p times delta. So then write this, just to be clear, this is just a polynomial algebra and infinitely many variables over z adjoin 1 on p. So you can just cancel the p's, and therefore we get that this operator theta 1 is just the usual p derivative operator. So there's nothing new there. But starting at n equals 2, everything changes. So what do we get? We get phi composed with itself 2 times is, now I'll just write this out again. We know theta 0 is E and theta 1 is delta. So let me just save some ink, if you like, by doing this. Then we get P times delta to the power P, keeping in mind that this is iterated multiplication, not iterated composition. And then we have P squared theta 2. So we're trying to solve for theta 2. We want to determine what theta 2 is as a polynomial in the deltas. But now we can expand, let's expand what phi composed with itself 2 times is in terms of the deltas. So this, we can write this as phi composed with e to the p plus p delta. And now phi is a ring. The Leibniz rules for addition and multiplication are the obvious ones. It acts as ring homomorphisms. So this is just phi of e to the p. In particular, it's additive plus that. But it's also multiplicative. So we can write phi of e to the power p, and using the additivity again, we get phi of delta. And e is the identity operator. So that's just the pth power of phi. Phi composed with e is just phi. And what's the next thing I want to say? Oh, yeah. And what is phi of delta? It's phi of anything is the pth power of that thing plus p times delta of that thing. So we get this. And now we can solve for theta 2. Wait, did I say something wrong? We can expand it. Let's expand it even further. So the pth power of delta, so this is phi to the p plus p times no, sorry. We'll expand this one. Oops. We'll expand this one further. So this is e to the p plus p delta, all to the power of p, plus p delta to p plus p squared delta composed with delta. And now, then we solve for theta 2. So observe this, that this here cancels, because now we use that these two are equal, of course. This cancels this, and this here cancels the first term in the expansion of that. And then we can divide by p squared. So what we get is that it's delta composed with itself twice. And then we have the sum. We'll do the binomial expansion, but the first term will disappear. And what do we get? We get p choose I e to the p I times p delta to the power p minus I. And then we have a p to the minus 2. So maybe another way of writing that, delta composed of itself 2 times plus sum I equals 1 to p. P choose I times p to the p minus I minus 2 times e to the pi times delta to the pi to the p minus I. So this is a there now. You see that this exponent here can be negative, but I is always at least 1. So I'm sorry, I is at most. Wait, what did I do wrong? I think I did my binomial expansion wrong. Oh, no,
You could have a p to the minus 2 over there, right?
I think let me. Sorry. So we 0 to p minus 1, e to the pi, e to the p minus I. Okay, I think that's right. And then so the point is that you're supposed to get 1 p, you have 2 p's here, you get 1 p always here, and yeah, it's worse when you have yeah, that's right. So when the exponent is when this thing is p minus 1, you get an exponent of 1 here, but that gives you have 1 p here and then 1 p here, and that, so you have no denominator here. And then for smaller values of I, it just keeps getting better because you have more and more powers of p coming from this exponent. In the last case, you have an exponent of p. You have no, p does not divide this binomial coefficient, but you have an exponent of p. So you still have no denominators. So therefore, theta 2 really is a polynomial with integer coefficients in those 3 operations. And this is exactly what gives you the rule for going back and forth between the two forms of the Witt vectors. There's the traditional, maybe I'll with the theta components. And then there's ours. And then there's a map between them, which I will either write down or I'll write down its inverse. Let me just write it this way to hedge my bets. Yeah, the theta components will, so it will send a vector A0, A1, A2, and so on to, the first 2 components are the same, right? Because theta 0 is the 0th iterative delta, and theta 1 is the first iterative delta. But beyond that, they're completely different. So this will go to, so now I'm writing out this formula in kind of a different way. So it'll be A2 plus the sum I goes from 0 to p minus 1, p choose I, p to the p minus I minus 2, A0 to the pi, A1 to the p minus I. And then the higher components are a big mess, and probably no one in history has ever written down explicitly the polynomial that says how you go from one to the other. So this will be an isomorphism of rings. So the ring structure here is defined in terms of this exotic ring structure, defined in terms of the Leibniz rules for the delta n operations. The ring structure here is defined in terms of the Leibniz rules for these theta n operations. Neither of them can really be written down in closed form beyond n equals 1, but we can prove they exist. And then this is a one has to prove. Okay, so yeah, let me I need to wrap
What
up.
happens to the delta structure in the traditional?
The delta. So that's a great point. So delta here is obvious. Delta is
Yeah.
just the shift. But here delta up here, delta is mysterious. I mean,
So that's the trade-off. Well,
yeah, yeah.
I don't know what the benefit is of the traditional bonding.
The two, yeah, maybe. Well, let's see. Yeah, it's good to kind of think of the pluses and minuses of the two different coordinate systems. Let me just quickly kind of say the key theorems, and then maybe we can talk about that or put it off to next time. So first, it's easy that the theta n generate this freely. This is simply because you see here that like it's kind of you just proved that by induction, and theta n can be expressed in terms of if you're allowed to divide by p, and you have all the previous variables, then adjoining theta n or adjoining phi is the same thing. So that is not a problem. What is so maybe, yeah, so what's the proof? So phi composed with n is equal to p to the n theta n plus lower order terms. And then you just then you do just prove it by induction. What's requires an argument, and this is the first time we've required this kind of a non-formal argument, but in this discussion, there's a lot of kind of brain-bending category theory, but it's at the end it's kind of all it's all formal. But here, this is a kind of a real argument using congruences. So one is that all the theta n's are actually integral. They don't have denominators. If you write them as a polynomials in the deltas, they have integral coefficients. And secondly, the theta n, in fact, generate delta as a ring freely. I mean, they're free generators. Even up here, so that's not the point. The point is that they do generate it. So they kind of obviously generate it with, maybe I should say as a, yeah, I said as a ring, but just to emphasize it as a Z algebra. So that's a real theorem, and the key fact to prove. So you again prove it by induction, and the key fact is that if you know the two sets of generators are the same up to degree n, then if you apply delta to the last theta, it's the same thing as theta n plus 1 plus lower order terms. So plus, let me be more precise, terms in z adjoin theta 0 to theta n. And then you keep applying that repeatedly, and you get that if you compose theta theta delta with itself n plus 1 times, you actually get theta n plus 1 plus lower order terms. And then you just conclude by induction. So adjoining theta n plus 1 to this is therefore the same as adjoining the n plus first composition of delta to that thing. But to prove this, you need some non-trivial congruences. I mean, they're not like super profound or anything, but it might, I could leave it as an exercise, but I would expect you to suffer a little bit over it. Every time, I've spent many years thinking about these things, and I always have to kind of figure it out for myself every time again. Okay. Yeah, I think now's time to stop. But I'm happy to take any questions if people have time.
So it's not clear to me why these theta ends came up in the first place.
Oh yeah, no, ask Witt. Like that's.
I mean, speaking of trade-off, what's the benefit?
Yeah.
Now delta is
okay.
not clear and multiplication is.
That's right. The one, I think the main benefit is that there's something called the Vershibung Map. So in theta coordinates, there's a map called V from Wn minus 1 of A to Wn of A called the Vershibung, which just means shift in German, and it shifts in the other direction. So it takes A0 up to An minus 1 to 0 A0 to An minus 1, and this is so this is certainly a well-defined function, but in fact it's additive.
What's Wn minus 1?
Wn minus 1, bit vectors of length n minus. Oh, I haven't told you. Yeah, right. Get to bit vectors of finite length later. We'll do infinite length. It just shifts to the right and then adds a 0. And the theorem is V is additive. I kind of think of it like an integration operator, like when with the differential bit vectors, remember these A's were coefficients of a power series. And now with a divided power series, and I want to shift them all to the right, which is kind of like integration. So this is it's an important operator. So it's not an operator in the sense of the delta ring operators. It doesn't act on any delta ring. It only acts on the bit vectors. So an important operator on W. But you can't describe it in closed form in terms of the delta coordinates. So can't.
So if we just look at differential rings, right?
Yes.
Is there anything interesting about the thetas then? I mean, is there something like a theta there?
I'm not aware of any. I mean, we could make something up, but there's so certainly you could have. I don't think this is what you're asking, but for instance, you could use the following sequence of operators. You could have the 0th derivative, and then the first derivative plus the square of the 0th derivative, and then you have the second derivative plus the square of the first derivative, and so on. These would obviously generate the ring of all differential operators, because the new one is just the second, the nth derivative plus a polynomial in the ones you already have. And there may very well be some people who work with differential operators who want, have some different generating sequence of derivatives of different orders. But I don't actually know any of them.
What about Vershibung? Does it have any?
Yeah,
said
right,
it's an
sorry.
integral, right?
Yeah, I don't. I think maybe, I mean, V, yeah, so V could be like the integration operator. And then that goes from these differential Witt vectors to differential Witt vectors. And it's additive, but certainly not multiplicative. I mean, I think this is an okay analogy. Like it's more just a cute analogy. It doesn't. I don't think there's any meaning behind it. But yeah. I guess it's in the sense that on differential rings, the natural operations are just polynomials in the derivatives. You can't naturally integrate. However, on the differential Witt vectors, you can naturally integrate, and it's similar with Vershibung. Vershibung is not a natural operation that makes sense on any delta ring. It only makes sense on the Witt vectors. So that's a sense in which they're a little bit analogous, and they're both kind of shifts.
Okay, so any other questions?
Okay, next time will be it'll be a little more concrete than this. I'll kind of get into the jet spaces and so on, back to the original question of kind of algebraic groups and things like that. Yeah, well, anyway, I just thought, since this one is a bit abstract, I thought I should say that.
I just want to ask, so when we will work with Witt vectors, we will be keeping this category theoretic notion that you gave, right? Not the traditional approach. Is that correct? I mean, when you will how does?
Yeah, maybe this. I think I will kind of really just be using what I said in the first lecture. Kind of these things for the most part will be sufficient. I might make some comments about this category theoretic approach a little bit, but I think the first lecture is more important to understand the third lecture than the second lecture is to understand the third lecture. I guess one of the points of this category theoretic approach is that there are kind of I didn't say this, but there are kind of three different ingredients. There's, on the one hand, the category of delta rings. On the other hand, there's the Witt vector functor. On the other hand, the third hand, there's this left adjoint functor. And actually, they kind of all determine each of the three determines the other two. And if each of the three has the appropriate structure. So just, in some sense, C modules determine the induced and the co-induced functors just by, well, they're the left and right adjoint of the forgetful functors. And you can kind of recover the category of C modules from this tensor product construction with enough extra structure, and similarly with the co-induced one. And you also can here. So maybe kind of the point of discussing this was that the knowledge of delta rings and the knowledge of Witt vectors are kind of just two different ways of looking at the same thing. That's not really present in the more traditional approaches just based on formulas.
Hmm.